Hey everyone, my name is Jason Rahman and I'm a software engineer at Microsoft. And today I'll be sharing about Linux scheduler tracing with Ftrace. So let's go ahead and jump in and talk about how we can do tracing. But first, some quick introduction. So I am a principal software engineer at Microsoft. Currently I'm working on Azure PostgreSQL. But previously, I was at Meta working on both MySQL and distributed file systems. I love learning about low-level operating systems and hardware. And in my free time, I'm actually an adjunct instructor for a computer hardware class and also do landscape photography on the side. So a few quick little highlights about myself. And so let's go ahead and jump in. So let's chat a little bit more about Linux scheduler tracing and why that can be important for our low latency applications. So first off, Linux actually has a really nice built-in tracing subsystem, and this is integrated into the kernel itself. There are trace points all across the kernel at various key points, whether it be in the system call path or, in our case, the scheduler. So there are many different scheduler trace points for things like whenever a process is switched out, whenever a process becomes runnable, whenever a process is paused. And based on all of these different trace points, we can actually reconstruct a full timeline of our application's execution. All of the different threads, when they wake up, when they go to sleep, when they're blocked, when they're woken up. And this is actually a really powerful capability that we'll see shortly. Now, we can configure the Linux Ftrace subsystem fairly easily. So there's a built-in tracefs pseudo file system built into the kernel. And you can see a couple examples here of commands that we can use to enable new tracing events. So by simply writing one into one of these special event enable files, we can turn on trace events for that particular trace point. Once we've recorded those traces, we can then read out the buffers into our own file for then later analysis. So the way that Ftrace works internally is that every single CPU in the system has a kernel mode per CPU ring buffer. As trace points are hit and events are generated, those events are then placed into these lock-free ring buffers. And each of these ring buffers is very low overhead. There is no locking, there is no cross-core contention. The events are placed directly into the ring buffer and then made available for use in the rest of the Ftrace subsystem. So there's very, very low impact on the rest of the running system when traces are being collected, which is important to get results that are accurate and representative of the actual running application. Now, once we have our data, we actually need to go visualize it, right? These traces themselves that we can collect from a running system are going to be very large in size. So we're talking dozens or hundreds of megabytes. So clearly, manual inspection of the trace events themselves it's not viable. So we can actually use a number of different user interfaces. So one that I have found personally useful is the Perfetto trace viewer. So you can see a screenshot here of what a Ftrace trace visualized in Perfetto looks like. So we can see there is a single track for every single CPU in the system. There's also a separate set of tracks below that show the timeline of every process and thread in the system as well. And using both of these, we can analyze the behavior of our running application. We can observe different thread transitions. We can observe threads being scheduled and descheduled and all of their life cycle events. We can see which threads even woke other threads up. And we'll see more examples of this later. Okay, so a quick detour. So we're going to talk briefly about some common server threading architectures, and then we'll actually trace a simulation of that architecture to see how Ftrace can be an incredibly useful tool to observe scheduling anomalies that impact our performance. So this is a pretty common pattern. So in a a common server application, we have an IO thread pool and a CPU thread pool. So the IO thread pool, we would typically have some set of threads that are reading and writing to and from the network. Right? These are meant to be very short-running, very low latency operations. So we have one set of threads that are specialized for that purpose. And then we have a separate set of threads that are meant to handle the actual heavyweight processing. So once the request arrives, the actual processing of that request is then handled on those CPU threads. And then, of course, on the response path, the response is sent back to the IO threads. And this is a very common pattern, right? We see this in Rust with Toke.io plus Rayon. Java, you have Netty for the IO threads, standard thread pools for your CPU work. And C++, we have like Thrift. I think gRPC probably does similar things. So this is a very common paradigm, right? So having non-blocking IO threads and then CPU-intensive worker threads. So once we actually have the work completed, we then actually have to hand off the result back to the IO thread. So it goes without saying that we actually have a fair bit of coordination between these threads. And each of these groups of threads has their own specific behaviors and performance requirements to achieve low latency. So the IO threads are typically cooperative multitasking. So these IO threads are going to be sharing the same thread with different connections, different requests and responses that are all being sent over different network connections. So we want to avoid any kind of long-running tasks that block that thread from being able to get its CPU time. And then we have short bursts of CPU. So when an IO is available on the wire as a request or a response needs to be sent out, we need to be able to quickly get CPU in burst in order to get that request into the system or to get that response back out over the wire. So it's very latency sensitive. On the other hand, CPU threads have a very opposite profile, right? So they're work stealing. You have a shared work queue. There's not much affinity of a particular connection to a particular thread the way you do with I/O. And these CPU threads have very wide range of CPU time, right? You might have very fast running processing. You might have very long running CPU heavy tasks. It's a very heterogeneous mixture of workloads on the CPU threads. So very different behaviors. And we see that will come through when we look at scheduling behaviors with Ftrace. So whenever we actually have an incoming request, we first read it off the IO thread. It goes onto the npm queue. Then a CPU thread actually has to be woken up. So in the critical path of a request being processed, there's often a thread wake up that has to occur. And we'll see in a little bit how this can be a latency issue using a scheduler trace. Also, whenever a response is ready to be sent, there's another thread wake up when the CPU thread pool has to now wake up the IO thread pool thread, which is meant to send out that response. Now, we can see that there are at least 2 different thread hops for every single request, and in reality, there are probably many, many more. Because in practice, that CPU-heavy work thread will likely be doing other downstream API calls, calling into databases, caches, all sorts of other operations that themselves require multiple other thread wake-ups. So another problem we run into is these 2 different workloads of IO threads and CPU threads can actually interfere with one another. Right? So IO threads have the need to quickly wake up and are very latency sensitive, whereas CPU tasks and CPU threads are really throughput focused, right? They want to occupy the CPU core for a long period of time, maximize their cache locality and cache reuse. And these 2 kind of run into tension with one another, right? And if you don't tune the system correctly with the correct number of threads, the correct scheduler settings, we can run into problems. And we'll see an example of that shortly. So let's try this out. So this is a very quick sample of how to use Ftrace to collect critical scheduling events, right? So we have 3 different scheduling events that we would like to collect: schedule waking, schedule switch, and schedule wake up new. So just as we mentioned before, it's pretty easy to set up these events. We just write this special event enable file. And once we do that, the kernel will then begin to trace those events into the ring buffers that each CPU keeps. Then we actually just reset the trace buffer and then turn tracing on. We sleep for some period of time, and then once we've slept and allowed those trace buffers to fill up, we can then dump those trace buffers out to our own file and then shut tracing back off again. So pretty straightforward, not that hard. It's easy to write scripts that do this, and there are other tools as well that can automate this for you. If you don't want to deal with all of this low-level file system stuff, you can also use BPF as well. So BPF has access to all of the same trace points that Ftrace has access to, but you can instead use BPF trace with a special format string that outputs events in the same format that Ftrace does. So you have your choice of how you'd like to record these trace events. But for the purposes of this presentation, we are focusing on Ftrace. Now, we have a load generator, right? So we have a very simple load generator. It's just a simple pulse width modulation load generator. So it runs for some interval of time, goes to sleep, wakes back up, and based on the desired duty cycle or the percentage of load that we wish to apply, we vary the amount of time that we sleep versus the amount of time that we run. So that gives us an approximation of this kind of wake up, work, go to sleep, wake up, work, go to sleep behavior that you see from your IO threads and your CPU thread pool threads. So we ran 3 different tasks on 2 CPU cores. So to simulate having a more resource-constrained environment, I just pinned these 3 tasks onto CPUs 2 and 4. The first task runs with a 10,000 microsecond period, and within that 10,000 microseconds, it runs for 4,000 microseconds. The second runs with a 5,000 microsecond period with 2,000 microseconds of runtime within that period, and the final one, 600 microsecond period and a 300 microsecond runtime. That last thread simulates our IO thread, right? Very short runtime, but it wakes up frequently in order to respond to various network events. And we see here that these 3 tasks combined only consume 65% of the total CPU in an aggregate sense, which is moderate to high load, but not outrageous. Right? It's not enough load that we would expect significant degradation in the system. And if we look here, we actually see some problems, right? So if we look at the blue thread on the top on CPU 2, that's going to be that IO thread that we discussed. And if we see here, it gets woken up at this location with that black diamond. So at that exact point in time, that thread wakes up and needs to get access to the CPU immediately in order to process an IO. But we see here that doesn't happen. Even though the CPU goes idle at the designated location, we actually don't get runtime until much later, right? We see 3.67 milliseconds of delay between when that particular thread wakes up and when it begins to run. And we can see at the bottom right, the scheduling latency detail is displayed here in the UI, and you can see that there's a roughly 3.6 to 3.7 millisecond delay between the thread becoming runnable and it running. So this is clearly problematic, right? There's a free CPU core available on 4, but yet this latency-sensitive task is left waiting for CPU. So clearly this is not a desirable behavior. So let's go ahead and keep analyzing this a little bit more. So the background to all of this, and the reason why we see this behavior, is that every CPU in Linux has a per CPU run queue. And this is modeled as a red-black tree. Every task or thread in the system has an entry in the red-black tree with its so-called V runtime as the key. So the V runtime is a measurement of how much runtime that thread has had. And the idea is that the kernel scheduler wants to take the leftmost task in this red-black tree and run that task. Now, each logical core has its own run queue, and only runnable tasks sit in the run queue. So what we seem to be observing here is that this particular IO thread that we saw delayed is on a run queue for a CPU that has another running task. and the kernel is not migrating that thread to a different CPU core. So we see this problem happening, right? So we have the first CPU number 2, that's running some other task. Task 3, which is our IO task, that last ran on CPU 2. But because task 5 is already running on CPU 2, task 3 can't run. And what we would like to have happen is we actually would like to have task 3 migrate and be load balanced over to CPU 4, which is now idle after a short amount of time. However, what we're observing here is that the completely fair scheduler is not actually load balancing. So this is what's called the overload on wake up bug. And this is actually a known bug. And this is actually something that the completely fair scheduler in Linux is known to have problems with. So there's this paper that was written at this point, probably 5, 6, 7 years ago. And the title sums it up: The Linux Scheduler, A Decade of Wasted Quartz. And if you want to dive deeper into some of these scheduling anomalies, you can go take a look at this paper. A couple of the bugs they've called out have been fixed, but many have not, including the one that we just saw. Now, this is not a theoretical concern. I have actually seen this in real production systems. So I've worked on storage systems and key value storage systems that actually saw 10 to 15 millisecond latency stalls precisely because of this issue. So this is not a theoretical concern, that there are actual real production workloads that have run into this issue and have had latency caused by this scheduler problem in Linux, so to speak. So, a bunch of lessons from today. So first of all, Ftrace is a very, very useful and powerful tool for detailed performance analysis. And it's easily accessible through TraceFS. We don't need a ton of complex tools. You don't need to download any sort of extra packages. It's available on any Linux kernel that's so configured. Very easy to use in production. Also, Perfetto. So Perfetto is a very nice, easy, lightweight trace viewer. It's built into your browser. It runs locally, so you're not shipping data off to any other machine. And it's very quick and easy to use. And then finally, based on Ftrace and Perfetto and our sample application, we have discovered some interesting scheduler bugs. And so now we know that the Linux scheduler has some pretty interesting bugs and poor behaviors for our sample applications. So in the future, if you have an application with poor latency, or you want to investigate the latency of your application in more detail, this can actually be a really useful tool for you. And I hope you can use it effectively. And finally, one thing to note is that CPU load is an average measurement. So the reality is that we need to use traces to understand fine-grained latency issues. So with that, thank you everyone for joining. And here's my contact info and details. Thanks, everyone.